Today we're going to be talking about special functions. Although some books may call these special functions, they're actually just more general ways to describe a very large class of functions. Okay, so before we start, let's go over what types of functions we've learned so far. Your very first function that you learned was a linear function, which had an x term, and then it would have a constant term. I'm going to write this a little bit differently because I'm going to be building up to a function called a polynomial, which is very general and takes this type of description. Okay, so this would be a linear function because it has an x term to the first power. Usually I would write m here, but I'm going to replace the m with an a1, but this whatever number goes by the x still counts as the slope conceptually. And then there's plus a constant term here with no x, and that would be like your y-intercept on a linear function. Okay, so first we learned about linear functions. The next type of function we learned about was a quadratic function. And the thing that was different about a quadratic function was the addition of a squared term here. When we went over quadratics, we called this one A, this one B, and that one C. But now I'm working up to where I have many terms. So I don't want to run out of letters. So I'm just going to call this A sub 2 because it matches the x squared term. It's the same A x squared from the quadratic. I'll call this A sub 1 because really what it's doing is it's matching the term x to the 1. And this one, A0, really it's called A0 because it's matching the term x to the 0. And you may recall that any number to the 0th power is equal to 1. So this is just multiplying 1, so that's the constant term. Okay, so this was your general description of a quadratic. And looking at the pattern here, if I wanted to go even higher, what would I write next? I would probably add a term to the third power because I had 0, first, second, third, and then I would need a number to say I want to multiply number times that, so I'll call that A sub 3. And then you can see that I'm just going to continue this on and on and on up until I get to whatever my highest power term I want is. So I'll call that A sub n, and I'll say that my highest power term that I want is x to the nth power. Okay, so this right here is called the general form of a polynomial. This is your general polynomial. Okay, it turns out that all the things that we've been learning so far, the linear functions, the quadratic functions, if it was cubed, it would be called a cubic. If it was to the fourth, it would be called a quartic. Then comes the quintic, etc. These are all your general polynomial functions, which is to say that they have positive whole number powers of x multiplying each one by a real number. Okay, so in your general polynomial, you can see that I put it up to a sub n, x to the n. Here, I would like to write my polynomial with the highest powers of x first, and then going down to the lowest powers in order. That will help me keep track of it the best. So I can see that my highest power of x here is going to be n. The highest power is n, and you see I have not put a number to the n because I want to be as general as possible. It's not really special, it's more general. So on a linear, the highest power is 1. On a quadratic, the highest power is 2. Now the highest power is n, and so we call n, we will call that the order, or sometimes you'll see it called the degree of the polynomial. Okay, and n is a real whole number which is positive, so if you have your highest power is 17, then you have x to the 17 in your function, and it's a polynomial of order 17 or of degree 17. Okay, and all the a's that I've been using, notice I've said a sub I because if I had 1 to the 50th power, I wouldn't have enough letters A, B, C. So I'm going to call them all a sub I, and those are the numbers that multiply the powers, and those are called the coefficients. So you can see that I've underlined a lot of different words on this board, and these are all going to be new vocabulary for the section. This is a general polynomial of order or degree n, and the a sub I are the coefficients that multiply it. Okay, so we'll learn a little bit about the polynomials now. We've got some facts about polynomials. And you may have noticed that when we were working with one linear function, we would only get one solution if we set it equal to 0. Then when we were working with your quadratic function, if we set that equal to 0 and use a quadratic formula, we could get at most 2 different answers. So going by that pattern, if you had a cubic equation, you could expect at most 3 answers. For a quartic to the 4th power, you could expect at most 4. My first fact about polynomials is that an nth order polynomial, which I'll abbreviate as poly, has at most n real roots. Okay, and remember the roots, aka the zeros, are going to be the values of x such that that equation is equal to 0. And if you have an nth order, you're going to get n real roots. So that's in line with what we learned about linear and quadratic functions so far. Okay, so that's my first fact about polynomials. My second fact is that, again, an nth order poly has at most, I'm not going to say n real roots again, this time I'm going to say n minus 1 turning points. Okay, so I just write the fact up here, and then we're going to go into some graphs of it so you can actually see what turning point means. But it's pretty self-explanatory. Maybe you noticed when we were doing lines, linear functions, it was always straight up or straight down or flat. It never turned, right? But then when we got to quadratics, that was the first type of function we saw that could have a minimum or maximum point. It had a vertex, which was a place where it turned. Okay, so a quadratic was a second order polynomial, x to the 2, and that second order polynomial had at most 2 minus 1, or 1 turning point. That's why a quadratic function has that one vertex. If I had a cubic function, which would be x to the 3, then I could have at most 3 real roots, and I could have at most 3 minus 2, or 2 turning points. So I could have a place where it peaks and then a place where it dips as well. Okay, so let's get to some graphs so we can actually see what I'm referring to as the roots and the turning points. Okay, so roots is already a thing that we've discussed before. That's not new vocabulary, but turning points is a new vocabulary, so I'll underline that as well. Okay, so let's look at some graphs of polynomials. Oftentimes I'm just going to write polys for short. Okay, so linear, quadratic, we've already gone over those, but let's say we have one that looks like this. Okay, what is the lowest order that I could say about this polynomial? Well, first of all, let's see how many roots it has. Can you guys see how many roots this equation has by the way that I've graphed it? Yeah, the roots or the zeros are the place where it intersects the x-axis right here. So you can see this one only has the one real root because it never intersects the x-axis again. Okay, so only one real root, so I would think maybe it's just a first order polynomial. However, that would be incorrect because a first order polynomial is just a line or linear function. I also have to look at the number of turning points. A turning point is any place where it changes direction. So like here it's going up, and then right here, all right, TP for turning point. That's a turning point because then it starts going down. And then down here, that's another turning point because then it starts going up again. So it has 2 turning points. And so now, again, if I wonder what is the lowest order polynomial that I could use to describe a picture like this, because it has 2 turning points, if I put the number 2 right here, the 2 will be equal to n minus 1, so the n must be 3. Okay, so it must be at least order 3. And order 3 means it would have a representation like this, a cubic term, possibly a quadratic, linear, and constant order term. And this is called your cubic function. Cubic because of the cube. Okay, so this one, we can determine that we must at least use a cubic to describe it. Keep in mind that the reason that you guys are studying all these different types of functions is because you are in a business, you have some real data to deal with. When you take a plot of your data, you wonder, what kind of function should I use to describe that? Because you need to have some sort of functional representation before you can use the mathematical tools that we've been studying. Okay, so if I had data, for example, I'll just show you a data example. Let's say my data looked like this, and then it looked like this again. And I wanted to try to match that data with a line or, some sort of functional representation. I don't want to just use a straight line because it doesn't look like it's in a linear pattern. Maybe I would want to use a quadratic, maybe an up-facing one, but an up-facing one wouldn't capture this kind of stuff over here. So if I just innocently wanted to draw a line through it, then I could draw this green line, and that matches it pretty well, and then I would know that I need a cubic. I would need to use a cubic because it's got those two turning points. Okay? You can also, though, use any of the other ones, any of the higher order polynomials. Let's say for the same data, I really wanted to capture the fact that it looks like it's going up, but then it goes down a little, and then it goes up again, and then it goes like that. What if I wanted to capture that fact, but using this green line, you see the green line doesn't do that. Let me draw another line in red for the same data. This would be a different fit that captures the fact that it goes down, and then it goes up again, and then it goes down, and then it goes up. Okay? So these two different lines could represent two different mathematical functional forms that I could use to describe the same data set. Which one's best for me? Whichever one is going to match it the best. Now, if I wanted to use the red line, what order of polynomial would I need to use? So pause the video, look at that red line, and try to figure out what is the least order polynomial that I could use to make that red line. Okay, so we're going to see how many turning points it has, and then we're going to add one to that, and that'll be our answer. Okay, so let's see, there's a turning point right here. There's another turning point right there, another one there, another one there. Let's count them up. 1, 2, 3, 4 turning points. If I had 4 turning points, that means I would need to use 4 plus 1, which is 5. So I would need what we call a quintic. You don't really need to know the names of them there, because as the numbers get higher and higher, the names might get weirder and weirder or not even exist. So we would just say we need a polynomial of order 5. And the reason we got the 5 is because it's 4 plus 1. It's got 4 turning points, so it must be a 5th order polynomial. Okay? So those are the facts about polynomials, and for a course in mathematics for business applications, you're mainly concerned about which type of polynomial leads to the best fit for your data. So I would say that you also want to see the link to the spreadsheet that I've given you guys. I've shown you a free spreadsheet program online, which you can enter your data into, and then I've given you direct and simple instructions on how you can take a data plot like this, a scattered plot of dots, and then find a way for the computer to create the equation for you, right? Because I would not expect you to be able to just look at a picture of a graph and then be able to say, oh, that's the equation. You can do that for lines connecting 2 points, but you can't do that in general. So in general, you're going to need technology to help you. So I would like to note again that I've given you guys a link on Canvas to a spreadsheet which gives you an example of some data, how to plot it in a scatter plot format like this, and then also how to obtain the equation of the best fit line. That should really help to get you going for your real-world applications, because in a business, most likely you just have a bunch of data points, you don't have an equation. But what I'm telling you is giving you tools on how to analyze equations. So how are we supposed to meet up? Well, that I would expect you to plot your data and get an equation, and then you can use the tools. Okay, please see that spreadsheet. That's very useful for the real-world applications. Okay, so the next thing we're going to do now is we're going to briefly discuss another class of functions. We just talked about the polynomial class of functions, and now we're going to move on to a new class which is called the rational functions. Okay, so the next class of functions that we'd like to look at past the polynomials is going to be called the rational functions. Okay, and rational functions are formed as a ratio. That's where the word rational comes from, is out of the word ratio, or as you might have seen, fraction, or a quotient of two polynomials. Okay, so let's say that we had one polynomial, p of x, another polynomial, q of x. Let's say that these are both polynomials, so that means they have that functional form that I just showed you. I can form a new function, which is the ratio of them. A ratio is the same thing as just dividing one by the other. It's taking a fraction or a quotient. So I will put p of x on top, divided by q of x, put q of x on the bottom. And the ratio of any two polynomials is known as a rational function. Okay, so let me just give you an example of what it looks like. For example, I could have x squared minus x plus 7 on the top, and then I could have x plus 4 on the bottom. A rational function will always appear as a fraction, and not only is it a fraction, but the top of the fraction is a polynomial form. The bottom of the fraction is another separate polynomial form. That's what defines a rational function. Okay, now rational functions have a little bit more interesting behavior than just your general polynomial, because rationals can have asymptotes. They don't necessarily do, but they can have asymptotes. And there's two different types of asymptotes, which I will show you guys in graph form. You may have heard of them before. They have a vertical asymptote and a horizontal asymptote. And we're going to discuss both of these briefly, but I also want to point out that for business applications, we mainly stick to the polynomials, and we don't use rationals that often. So as I go into the vertical and horizontal asymptotes, don't get overwhelmed by all the information that I'm trying to give you. Okay, so let's start with the pictures, because the pictures will be easier than the equation forms, and we will discuss the vertical asymptotes first. Okay, so vertical asymptotes, I will abbreviate that by VA, if you see me write VA. I'll show you what it looks like in a picture, and maybe you've seen it before. Have you ever seen a graph with a dotted line going vertically down the graph at some point, and then maybe you have a function that looks like this? Okay? Usually when you see a vertical dotted line plotted on the function, that means that the function is having some strange blow-up type of behavior. It's either increasing or decreasing without bound. So this is what we would refer to as unbounded behavior. A bound means that it has a possible highest real number that it would reach. But here you can see that on the left side of this equation, this function is getting bigger, 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 higher, higher, and it's going all the way up to infinity, and so it's increasing without bound. So you'll see it referred to as increasing without bound, or also you can say that it's going to plus or minus infinity. Or minus infinity. It might be going to plus infinity, it might be going to minus infinity, it might be doing a little bit of both. So let me show you some different examples, all of things that could count as a vertical asymptote. Okay, and the vertical asymptote could appear here for positive value of x. It could also appear here, it could appear over here, it could appear for any value of x. What defines a vertical asymptote is the fact that the function is decreasing or increasing without bound. So you can see this one is going towards negative infinity, and this one is doing a little bit of both. Okay, so on one side it's going to positive infinity, on the other side it's going to negative infinity. Whenever it's blowing up like that, it has an unbounded behavior. We will refer to that as a vertical asymptote. Okay, this is why having a graphing calculator and knowing how to use it is so important, because if I give you a function such as this r of x right here, I would like you to investigate it graphically. Take a graph of the function and see where the vertical asymptote is on the function. Okay, actually we've already learned this a little bit in a previous lesson on domains, because vertical asymptotes are not in the domain of a function. Remember, all the way back from the beginning, A function is defined as a rule which takes a real number in and then it spits a real number out. Okay, and the graph is a graphical representation of that. Everywhere I put a real number in right here, it would spit a real number out. But right here, it's going to plus or minus infinity, and infinity is not a real number. So if I put in this number for x right here, let's say that x is equal to 2 right there. If I plug in a 2 right there, I'm going to get some sort of blow-up behavior. That's not a real number, so that means x equals 2 cannot be in the domain. Okay, so keep in mind that if you do have a vertical asymptote, it's equivalent to the place where where the x value is not in the domain of the function. Okay, so let's try a little bit of review right now. Take a look at this function and tell me what special value of x is not in the domain of this function. X equals minus 4, that's right. So it turns out x is equal to minus 4 is not in the domain, and that's actually the location, if you graph it, of the vertical asymptote. Okay, so vertical asymptote occurs when the denominator of a rational function, remember a rational function is a fraction, polynomial on top, polynomial on the bottom, and the bottom, the denominator, when the denominator is equal to 0. Okay, because when it equals to 0, then you're in a divide by 0 scenario, and your function is most likely blowing up. The only exception to that is if you're dividing by 0 on the bottom, and you actually happen to get 0 on the top as well. That's known as an indeterminate form. That's a little bit beyond the scope of this class to really discuss that in detail. You can see a class on calculus or pre-calculus for that. Okay, so what you want to know though here is that vertical asymptotes occur when the denominator is equal to 0. Okay, so now if you're going to define, as I did before, a rational function as a quotient or ratio of two polynomials. The polynomial on the bottom is q of x, so these occur at the zeros of q of x, okay? So vertical asymptotes occur at the zeros or roots of q of x, and those are the x values such that when you put that value of x into q, you're going to get 0 on the bottom. That's bad. You don't want to do it, you want to avoid it, and now you know graphically what it appears as on a graph. So if you see that on a graph, consider what kind of function you're graphing. Why is that happening? You're probably dividing by 0. Okay, so that's the vertical asymptotes. So now I'm going to go into the horizontal asymptotes. I'll say that it's a bit unfortunate that both of these things are referred to as asymptotes because it's misleading to students. Both of these things are separate questions. Okay, vertical asymptotes we saw are a bad place. They're a place where your function is blowing up with unbounded behavior, and horizontal asymptotes are a completely different concept, which also falls under the word asymptote. And here I'll abbreviate horizontal asymptotes as HA. Okay, these represent your long-term behavior of a function. Okay, so usually in business applications, your function, your x variable is like the number of units. So usually you're going to consider this as how the function behaves for a very large number of units. Because usually x, like the x units, is the value, okay? So I'll give you an example, just a picture example here. Let's say that we have a function that looks like this, okay? Maybe this is like our profit function. Now, you may or may not have noticed that whenever I draw a polynomial, the thing about a polynomial is for very large values of x, a polynomial always increases without bound. Polynomials will always blow up to positive infinity or they will go down to negative infinity. There's no way for a polynomial to like top off at some value like this. You see how this function is kind of approaching and why it's kind of for long terms x as the x gets very, very large, just kind of topping off like that, that is something that you need a rational function or a different type of special function to behave. Okay, so this topping off at a specific y value requires a rational function. Or another type of special function like an exponential form. We haven't studied those yet, so that's why I'm saying requires rational function under the set of functions that you guys know so far. Okay, so you can't get this topping off type of behavior from a polynomial. You need to make a ratio of two polynomials. I'll erase this. Let's say this represents profit, cost, any of the revenue, anything like that. But I don't want to confuse you to think that it's a polynomial. This must be a rational function because it tops off. Okay, so again, horizontal asymptotic behavior represents what happens to the function, as x is getting very large. Okay, you want to look out here for the horizontal asymptotes. Okay, that's the difference between the horizontal and vertical asymptotes. You see, when you're looking at a graph of a function, to find the vertical asymptotes, you find the place where the function blows up. It's crazy, it's going up or down to infinity. For a horizontal asymptote, you're not looking for places like that anymore. You want to go all the way out for very, very, very large x, like x equals 1,000,000 or 1,000,000,000, and see what happens to your function. Is it topping off? Is it tending toward just one specific value? That is known as a horizontal asymptote. Okay, so horizontal asymptotes have a functional form like y is equal to some limit L, as opposed to a vertical asymptote, which is a special value of x. Like we saw in the last example, x equals -4. So that's the difference in the functional expressions of them. Okay, so why would you care for business? I was trying to think of this myself. Let's say you're starting as a small business and you're just doing a small number of units. Then your business grows, and it's growing larger and larger and larger, and you're really scaling up till you're doing hundreds of thousands of units. What's going to happen to your profit? Is your profit increasing without bound, or is it tending towards some special amount? That's when you would consider a horizontal asymptote in terms of business. Okay? So for polynomials, we have 3 different cases for the horizontal asymptotic behavior. Okay, so let's just go over this. Sorry, not polynomials, for rational functions. Let's say we have a ratio of 2 polynomials, p of x and q of x. And let's say that p of x has the order n. And then q of x has the order equal to m. Okay, so we just introduced the concept of order. The order of a polynomial is the very highest power of x that we see. Okay, so let's say on top, the very highest power of x that we see is n. On bottom, the highest power of x that we see is m. Now we're going to compare which one of these polynomials, on top or bottom, has a higher power, and that will determine what type of horizontal asymptote, if any, is going to occur. Okay, so we'll start, there's going to be 3 different cases. Case number 1, if m is greater than n, this would be the case where the polynomial on the bottom has a higher order, the polynomial on the top has a smaller order, and so the function r of x, if you have like a higher power on the bottom and a smaller power on the top, when x gets very large, the r of x is going to go to 0. And this is always for very large x. Horizontal asymptotes, again, are considered in very, very large x values. It's actually the limit as x goes to infinity. Okay, so your rational function, the ratio of those 2 polynomials, will go to 0 if you have a higher order polynomial on the bottom. Kind of makes sense because higher order polynomials, the numbers get much, much bigger. So then you'd have a bigger number on the bottom, so it should go to 0. Okay, number 2, let's say if m is less than n, this is going to be the opposite case where now we have a higher order on top, so we'll have a much bigger number on the top, and then we'll have a smaller number on the bottom. So what do you think will happen there? For large x, again, this is going to be for large x, it turns out it's going to either go to plus infinity or, not divided by, I don't want to confuse you, it's going to be either plus infinity or minus infinity. That'll depend on the leading order coefficients, so what kind of numbers are multiplying those polynomials, like -7 or +3 or whatever. This is the case where you have a bigger number on top, smaller number on bottom. It must blow up to infinity or minus infinity as your x gets large. Okay, your third and final case, well, either m is greater than n, m is less than n. Last case, m is going to be equal to n. This would be the case where you have the same order polynomial on top and bottom. Like you have a quadratic divided by another quadratic. Okay, this is the case of a non-zero horizontal asymptote, where your r of x is going to go towards some limit L, but the L is not going to be 0. Okay, the case where the L, what it tends toward a 0, is under this first case. In this third case, this is actually the one that I've illustrated here. The L is a non-zero real number, and actually L is determined, L is the ratio of the leading order coefficients. And I'll show you what that means as an example, so you can actually see that in action. Here, L is going to be defined as the ratio of the leading order coefficients. So for example, this function that I've drawn right here, this must be the case. I can see for very, very large x out here. I'm looking all the way out here for my horizontal asymptotes. This is a case where I'm going to a non-zero real number. So I must have the ratio of two polynomials of the same order. So let's say I have it like this, and then maybe like that. Okay, I'm kind of just making this one up. I'm not sure if this function actually exactly looks like this, but I know that this function right here, as x gets very, very, very large, if I plugged in very large numbers for x everywhere here, I would know that this function is tending toward a real number that's not 0, because the orders, do you know what the orders of these polynomials are? Both of these are of order 4. Okay, so these are two quartic equations, x to the 4 here, x to the 4 there. So the highest order terms match, and so then I know that the horizontal asymptote for x getting very large is y is equal to 3/2. Now you can see what I meant by the ratio of the leading order coefficients. That's just a very fancy way of saying you find on top and bottom the two powers that match, the highest powers, and then you take the number from this one and the number from that one, and then just make the fraction out of it. Okay, so it's a fancy way to say something that's pretty simple. You just put the 3/2. The horizontal asymptote is 3/2. Okay, so that should help you to figure out horizontal asymptotes and vertical asymptotes of functions. Before we move on, let me just give you guys a picture and ask you to describe where are the horizontal and vertical asymptotes of the function. Okay, so let's see. This is number 1, and let's say that this is a height 4. Okay, so here's a number 1 right here. Here's a height 4 right here. What is the horizontal asymptote? What is the vertical asymptote? Pretty self-explanatory because they have the words vertical and horizontal in them, right? Keep in mind, that should lead you to the answer. Where's the vertical dotted line? X equals 1. That's an x value, so the vertical asymptote is x equals 1. Where's the horizontal dotted line? Y equals 4. So the answer for horizontal asymptote is y equals 4. Okay, so keep in mind that when asked for vertical or horizontal asymptotes, vertical comes in the form of x equals a value, horizontal comes in the form of y equals a value. Alright, so let's move on to our final type of special function, and that is going to be piecewise defined functions. Out of all the functions that I've done in this lecture, well, polynomials is probably your most important. Rationals for business is maybe your least important. And another pretty important and pretty common function that you're going to see in business is known as your piecewise defined function. Piecewise defined functions. These are the type of functions where I can't just use one equation to define them because they make like a kind of a skip or a jump somewhere, and so I can't just use one polynomial. Let me show you a picture. I actually got this example straight from the internet. This is a real life example. I looked up how much does it cost to send a letter through the United States Postal Service versus the weight of the letter. Okay, so the X value here is going to be the weight of a letter in, I think it was ounces. Okay, let's call that the X. And then over here, P, this is going to be the price to mail the letter via the United States Postal Service. Okay? I looked it up and it said, well, if your letter is 1 ounce or less, it's going to cost you 49 cents, okay? So if your letter is 1 ounce or less, it's going to cost you 49 cents. Oh, P is the price, but I want to use this for the Y values now. Okay, then it says if your letter is more than 1 ounce, up to 2 ounces here, then it's going to cost you 71 cents. Okay, 71 cents. Then if your letter is between 2 and 3 ounces, it's going to cost you 93 cents. So it gets more and more expensive as the ounces increases of the letter, and then there's more instructions for heavier letters. Sometimes it gets into different instructions, like now it's a package, not a letter. Let's just stick with this, and we'll see how this is defined mathematically through a piecewise definition. So looking at the picture, you can see that every function I've told you about so far is not going to work for trying to draw this picture because it makes these jumps like this. So I can't use a polynomial or a rational to describe it. So what I need to do is describe the price of mailing that letter in different pieces. You see there's 3 different skips right there. So I need to, well, there's 2 skips and there's 3 flat lines. So I'm going to have to categorize this. A piecewise defined function is basically a categorization of what output you want the function to make for a different input. So the categories that they broke it down to in was if your letter is greater than 0 ounces up to 1 ounce. Then if your letter was greater than 1 ounce up to 2 ounces. Then if your letter is greater than 2 ounces up to 3 ounces, and then we'll stop. There's other instructions for heavier ones. Okay, this costs 49 cents, this costs 71 cents, this costs 93 cents. Okay, so that is an example of a piecewise function. You can see the mathematical definition on this side, and you can see the corresponding illustration as a graph on this side. And now mainly we're going to be focused on the mathematical representation, and if you're given this, how can you figure out what it looks like? How can you figure out different functional evaluations? For example, I might ask you to evaluate what is P of 1, what is P of 0.5, what is P of 2.4. I need you to evaluate these values. You can use this equation here, or if you want, you can look at the graph. Go ahead and pause the video and try to evaluate these different parts of the function. Okay, so mainly on a test situation, you're going to be given the mathematical definition. So make sure you can do it from there. P of 1, this is the input. I just have to go over to this set of instructions and see what category does the number 1 fall under. Now this equal sign right here tells me that if x is equal to 1, this is the category for it. So the answer is 49 cents. Okay, so again, every time you get an input, you just go and you look, what category does that fall under? 0.05. That's between 0 and 1. So again, still 49 cents for that tiny little letter. What even would that be? 2.4. What category is that under? It's bigger than 2, smaller than 3, so the answer right there is 0.93. Okay, so when you're working with a piecewise defined function, you just look at your input for x, and then you consider what category did that fall under. Okay, let me show you one more example of that, and that will conclude this video. So this one example that I just showed you from the post office, that was a function of the total price of a letter as a function of how much the letter weighed. Now I will do another example as a per item pricing. So this is different than the last example because this is going to be your pricing per item, and this is a common thing people would do in business. Let's say you want to encourage more people to buy your items, so you're giving that bulk discount, similar to the bulk pricing that you saw me approximate with a linear function from before. Let's say in my business, if you buy 5 or less items, it's going to cost you $3 each. But I want you to encourage to buy more. So if you buy 6 to 10 items, I'll give you a price of $2.75 each. That's why I meant pricing per item. And let's say if you buy more than 10, I'm going to give you a price of $2.50 each. That's going to be your best deal. So buy more than 10. What I'm looking for here, as this example, is for you to write down what is the price as a piecewise defined function. Okay, so from what you just saw, we have 3 different categories here. For each of these 3 categories, you want to describe them in this column over here as what values of x fall into that category, and then what's the output of the function, you're going to put it here. So pause the video and try to fill out the piecewise defined function. Okay, so what I would do to do this problem is I would start with the category part, the column over here on the right. Buy 5 or less. That means that I bought 0 all the way up to 5, including 5. You want to be careful here with the underline. Is 5 included in that category or is it not included? Okay, so I would put this underline here because it says buy 5 or less. If it said buy less than 5, specifically less than 5, then 5 wouldn't count, and then I would get rid of the underline like that. Okay, so this is what it would look like if it said less than 5, and this is what it would look like if it said 5 or less, and the difference is whether or not you included the number 5 into that category. Buy 6 to 10. So that means between 6 and up to 10. Okay, so notice that this is a little different than our previous example. In our previous example, the number of ounces of a letter could be any real number. In this case, the number of items must be a whole number. I'm not selling items in the half or a quarter of an item, so it's okay that this 5 and the 6 do not match. That's just because for my domain here, my x must be a whole number. By more than 10, that means my x is going to be strictly greater than 10. Okay, so I could put greater than 10, or from what I just said, just for this problem, I could have said x is greater or equal to 11 because it has to be in whole numbers. Okay, so that's something that's special about this example, is that in this example, the domain is x is a whole number, as opposed to last time when the x was any real number. Okay, so that is the column that describes how the input is categorized, and that's how you would start. And then afterwards, you're going to want to put what kind of output comes out. So buy 3 or less, that's going to be price of 3 each. Then it goes down to $2.75, then it goes down to $2.50. So there you go. I just fill it out just like that. And if you wanted to consider what that would look like as a graph, then you would just see a bunch of straight lines, like here's 0 to 5, here's 6 to 10, and then here's greater than, this is 6 to 10, and then this is beyond 10, so I just need it like that. Okay, so the price per item would be like $3 up to number 5, and then it would shoot down that from 6 to 10, it's going to be $2.75, and then it's going to go down to $2.50 when I get greater than 10 and beyond. Okay, so that would be a visual representation. And then to see that the domain x is a whole number, really you would just want to visualize just the whole number points on these lines. Okay, so let's take this piecewise defined function, and I'm going to test you a little bit. This is going to be similar to what you're going to see on your upcoming midterm here. There's a question like this. What is the price per item? What's the price per item if I buy, let's say, 7 items. Okay, so try to answer that question. I'll call that question A. And then B, now I'm going to ask you a little bit of a different question. What is the total price? Not just the price per item, but the total price if I buy, let's say, 20 items. Okay, and then this is just testing to make sure you understand the relationship between per item price and total price. So go ahead and pause the video, try to answer these 2 questions. Okay, so price per item, that's actually what the function is defined as. So the answer for a price per item question would be just take the 7 and go here and say which category does 7 fall into. Goes right there. So the answer is the output right there. So $2.75, and that's the per item price. Okay, so that would be the answer there. And then I hope you didn't get tricked on this question. The total price, if I buy 20 items, how much was it costing me per item? That was the best category where I got the best deal, $2.50 per item. But the answer is not $2.50, it's $2.50 times the 20 items because I want to know the total price. So the total price was $50 for all the items all together. Okay, so if you see that question, you might see that on the practice midterm and the upcoming midterm. Make sure that you carefully differentiate between what the question is asking.